Okay, everyone. So we're going to look at these shift mechanism diagrams again, like we did in yesterday's lesson. So effects of volume changes, so very similar. So you're going to look at what is causing a shift, what is increasing in terms of rate, and then of course the overall impact is going to reach a new equilibrium, but it may be greater or less than what it had originally begun with. So over here, let's say we had this situation and there's a decrease in the volume, which means we have an increase in the pressure. So remember, in general, when you're going to decrease the volume, all of the concentrations are going to increase. So you're going to have more particles per space, whether that's a solvent or if that is a just empty space, right? So your equilibrium at the end should be higher than what it was at the beginning. But of course, decrease in volume, you compare. So we have 3 versus 2. So if we have less available space, it will shift towards the direction that's going to occupy less space. So in this case, you're going to have a forward shift or a shift to the right, right? The forward rate is going to be going faster. So what ends up happening is, of course, the forward arrow should be larger, but then the end position should be higher than where it was at the beginning. If you are giving this less pressure, more available space, it should be the opposite. You would have a concentration, or I should say, your rates at the end will be less because you're going to have less particles simply there to begin with per area. Okay, so let's take a look. So explain in terms of forward and reverse reaction rates how the equilibrium system below would respond to a decrease in volume. So decrease in volume, increase in pressure. Okay, so here we have 2 versus 3. So if we're going to be doing this, we're going to be occupying, we want less space, so we want to try and lower the pressure. So in this case, it would shift towards the left. So the reverse reaction, reverse rate will increase more than the forward rate. But the net overall should have an increase, a net reverse shift, but the end result should be higher concentrations than what you had to begin with, right? Number 2, explain in terms of forward and reverse reaction rates how the equilibrium system below would react to be diluted. So we have more available solvent volume, right? So you're comparing the number of, in this case, ions. So we have 1 versus 3. So if it's being diluted, we want to occupy more ions in that available space. So we would shift towards the right. So the forward rate, will, so what's happening here is actually both rates are slowing down because you're going to have lower concentrations. But I guess a way of thinking of this is the forward rate will slow down less than the reverse rate. The reverse rate would slow down, if you want to think of it that way, right? So it's like, imagine originally if you had this, then the shift that would be caused is something along the lines of this, right? So then the end result will be less than what it was, but the forward, I guess, will still be decreased, not as much as the reverse, because it's going to occupy more ions, right? But overall, if you are going to have less particles per unit area, you're going to have lower rates than what you started with. Just like the other one, right? If we were to look at this one, we would have a reverse rate increase, but both of them would actually increase. So what would happen would probably be something along the lines of this. Ooh, maybe let's make them a little bit more drastic, right? But they actually should be higher than what it was before. Maybe I'll make that a little bit more to make more sense. Okay, but it should be more than what it was initially because the concentrations will be higher. There's more particles present, right? So the rates are naturally happening faster because they're going to be colliding more frequently. Okay, so let's take a look here where we have now these, so we're drawing the shifts and we also have that rate graph that we saw from yesterday's lesson as well. So we're going to show how will the forward and reverse reaction rates respond to a sudden compression at the system at time 1. Use a solid line for the forward rate and a dotted line for the reverse rate. Okay, so compression. So we have lower volume, increase in pressure. Here we have 3 versus 2. So that means we're going to have a shift towards the right, or the forward reaction, right? So no matter what, at the end result, our equilibrium is actually going to be higher, right? We already know that. Because we're going to be increasing, it's almost like you're increasing the number of particles. I don't want to say concentration, because we're not measuring concentration, we're measuring rate. But if you have more particles there, they're going to find each other more easily because they're in a smaller space together, right? Like they're just going to collide more, so the rates will naturally go up. So the shift, though, will be an increase in the forward more than the reverse. The reverse is still going to increase, okay? But the forward will increase more. Maybe let's make it something like that, right? To show it as more of an effect. But of course, the end result will be higher. Now, in this case, when we're drawing with these rate graphs with the dashed line and the straight line, you're going to have an increase in both, okay? But the forward reaction is increasing more. So for the solid line, you may want to increase it, a spike up. The dashed line will also go up, right? But obviously not as drastically, but it will meet that new equilibrium. And notice it's going to be at a higher position than what it began at. So both are increasing, but the forward is increasing more so to try and relieve that pressure. Okay, so now on to a completely kind of different stressor. We're looking at how temperature stresses are affected with equilibrium shifts. So temperature changes. So we have to kind of recap here what an endothermic and exothermic reaction are. Maybe before we even do that, I'm going to add in a new thing. Okay, so remember, exothermic reactions have and we have seen how this is written, right? Some sort of energy amount, okay? So energy is released from the system when you have an exothermic reaction. Endothermic reactions is where you have energy being put into the system from the surroundings, right? So this goes back to the last unit that we just did, right? So depending on if you have an exothermic or endothermic reaction, the shifts in your equilibrium are going to be a little bit different. Now, the easiest way that I find for students to understand this is to think of energy as being part of the chemical reaction. Okay, obviously we know that it's not matter, there's no atoms in it. But if you think of it that way, it actually will make a lot more sense because it's going to seem similar to when we looked at yesterday's lesson with concentration changes. So for example, let's look at the ones here just that I've written out. If you have an exothermic reaction and you add in energy, like I'm going to make this hotter, I'm going to add heat. That's like the same thing as saying you're going to add in a product. Like I'm going to add in C. So what it will want to do is try and relieve whatever addition you've just done. So because energy is on the product side, it's going to shift to the reactant, right? The reverse reaction is going to increase because it wants to try and get rid of that extra energy you've just put in place. And remember that the opposite reaction is always the opposite function. So if the forward reaction is exothermic, the reverse reaction is endothermic. And we saw those with the potential energy diagrams, right? So let's say we had an endothermic reaction and we were to remove heat, like we cool it down. So this would be the same thing, like as if I were to decrease A, like we lower the concentration of a reactant. The reaction is going to want to replenish whatever it was that you took away. So if we took away energy, or we took away A, or we took away B, no matter what, the result is always the same. It's going to push to the direction where it can replenish whatever was removed. So in this case, it's going to shift to the left. The reverse reaction will then speed up. So if you think of the energy as being part of the reaction, it literally is the same idea of when we added or removed the reactants and products from a reaction. Okay, I just find it's easier to think of it that way. But of course, we know we're dealing with energy. Okay, so here we have our little general idea here. So a really weird star. Okay, so equilibrium plural, okay, respond to changing temperatures by shifting to remove some of the added kinetic energy, which is usually heat, or to replace some of the removed energy. So if you take away energy, it's going to try and replenish it. If you add in energy, it's going to try and remove it, right? So if we look at an endothermic forward reaction, if you were to increase the temperature, right, it's going to be causing a shift towards the products. So let's see if this makes sense. So if we have endothermic, B plus, I don't know, 25 joules making C. So, pardon me, if we increase the energy by adding more heat, it's going to shift forward to try and use that up. So you should have an increase in the products and a decrease in the reactants, which is exactly what it is here. Now notice, there's no dramatic spike up or spike down here, okay? So when you're doing temperature changes, it's more of a gradual change instead of a, remember with concentration, it was like literally like you have an equilibrium, there's a spike, right? So there's no spike here with temperature changes. So that's maybe one big difference. The idea is the same, but that's one difference, is that it's not a dramatic spike. It's like a change in concentration, not super gradually, but curved, right? Not like a spike up. Like it's not like you're pumping some in or you're like dramatically decreasing it down. Okay, so exothermic reaction, right? So that means you have energy in the product side, right? So if we were to increase the temperature, that's like the same thing as saying we're going to increase a product. It's going to shift to the left to try and use that energy up, right? These should be equilibriums. So what ends up happening is the products are decreasing, right? The reactants are increasing. So it should kind of make sense with what we've been talking about. Okay, so let's look at this next problem. So we have the system below is heated. Okay, so we have temperature increase. So let's check out what they're telling us. So we have negative 198, kilojoules per mole. So that means this is exothermic, right? So it'd be like the same thing if I wrote here plus energy, right? It's exothermic reaction. If we are heating it up, that's like we're adding in a product. We're adding in additional energy. So the shift that's going to happen here is it's going to shift to the left. So what will happen is the endothermic process, or the reverse reaction, the rate will increase. Okay, and then of course we'll have less product, like the product is going to be decreased and the reactants are going to be increased here in this particular case. Okay, so the system below is cooled. So here they're actually writing it in for us. So if it's cooled, that's like saying we are removing some of that energy. So in this case, you're going to shift to the right, right? So we're trying to replenish that energy. So the forward rate will be increasing, and you'll have more product being made, and then your reactants will then lower. Okay, so I'm going to leave this very last part to the next part here, part 3.